Start the recording. So we have, if you've been counting, 4 different notions of limits right now. We have the limit of a sequence. We have the limit of a function. We have pointwise limits of sequences of functions. And we have uniform limits of sequences of functions. So that's 4 different concepts of limits. Today we're going to show how that last one is actually the same as the first one. So we're going to show how uniform limits of sequences of functions are actually just limits of sequences in a different metric space. Okay? So that's our goal. To do this, we need to restrict our attention to bounded functions. So we defined this Monday, what it means for a function to be bounded. So we're just going to make the following definition. Given metric spaces x and y, we are only going to look at the set of bounded functions from x to y. Okay. That's our set. Functions that aren't bounded, we're not really going to be able to say anything about today. Okay. So, I mean, if you want to consider a function that's well, it's not bounded, you should restrict the domain to make it bounded, basically. And remember that if you have a continuous function and you restrict the domain, you can always make it bounded, okay, if it's continuous. And we care the most about continuous functions today. Just a little remark here. This set, if y is just we don't even care what metric is on it. If y is the real numbers, then what are we looking at? So I guess let me not write it that way. Let me just write it this way. This guy, the set of bounded functions from some metric space x into the reals, that's a vector space. It's a vector space just because it satisfies the vector space axioms. You can add two bounded functions together, you'll get another bounded function. You can multiply them by scalars. Okay. What's the basis for that vector space? A basis for that vector space. Yeah, never mind the basis question. That's a difficult question. But in fact, we can generalize a little bit more even. If our codomain is a field, then we've got a vector space. Okay. If that word field is unfamiliar, don't worry. It doesn't really matter. These are just comments. Okay, so anything we can do in a vector space, we could do here. Yeah, okay, so Ben asks, what are the scalars? The scalars are, in this case, the reals. In this case, it's the field F. So I should maybe write, this is an F vector space, or a vector space over F. Okay, what was I saying? Yeah, so this is not really important today. I'm just pointing out that you can't think about this as a metric space. Oh, sorry, as a vector space. What's important today is that it's a metric space. Okay, so here is our observation. If we take two functions in this space of bounded functions from x to y, okay, if we look at the set, I'm going to look at the distance in the codomain between the function values at every point. Where is that set? What's in that, or like what type of thing is in that set? Just so we're on the same page.
A real number.
Yeah. This is, a bunch of distances. So it's a bunch of reals, right? In fact, it's non-negative reals. So here's the point, the observation, is that if f and g are both bounded, then that set is also bounded. And we really only care that it's bounded above. In the lecture notes, I'm going to leave this as an exercise. You really just have to chase through that definition of what it means for a function to be bounded. But there's some point where f is in a ball centered at, well, I mean, f is in some ball, g is in some ball, so together f and g are together in some ball, and then the maximum distance would be twice the radius of that ball. Okay? Any questions so far? Okay, well, I hope you see where this is going. We've got a set of real numbers that's bounded above, so we can take a supremum. And that supremum is the metric. So this is our definition of the uniform metric. F and G are bounded functions from one metric space to another. And we are going to define the uniform metric by, we're going to denote it a d sub infinity. and it will be the supremum of the set of distances between F and G. Okay. I said we're going to call it the uniform metric. We should prove it's a metric. Hold on to that thought for a second. That'll be the first thing we do. The other thing is the notation d sub infinity. That infinity we've seen that before, right? So we saw an infinity metric on Rn. Okay. This is really the same. It's really a generalization of that metric. Okay. And we could also define a D1 metric on the space of functions, or a D2 metric, etc. To define those metrics, we would actually have to integrate the functions. The functions would have to be integrable. We'd integrate their differences, etc. Okay? So those are actually much more complicated definitions to give in this setting. But the D infinity metric is a lot easier to give. It's just the supremum of differences. Okay? But it really is just a generalization of the D infinity metric we've already seen. Not that we're going to use those facts here. Okay? So our first thing to do is to prove that it's a metric. Who remembers the metric space axioms?
Well, it needs to be 0 if and only if two functions are equal. It needs to be positive in all other cases. Mm-hmm. And you need the triangle inequality.
We also want it to be symmetric.
Mm-hmm. Okay, is this function 0 if you plug in, is d infinity of ff 0? Do this in the upper right hand corner. Right, well, you plug that in. You're looking at the distance between f of x and f of x. That's always 0, so the supremum of that set will be 0. Okay? Is this function always non-negative? You got a set of distances here. Distances are always non-negative. So when you take the supremum, that's also non-negative. Okay? Is it symmetric? Yes. If we swap f and g, that doesn't matter because the metric on y was symmetric. Okay, so everything's clear except for maybe the triangle inequality. Let's prove the triangle inequality. Okay. We've already just kind of verified the others. If you want to write down a proof, that's fine. You can do that on your own. Okay, so we need to take 3 functions. We'll call them f, g, and h. Now, really the only thing we have to use is that we've got a triangle inequality on y. So let's pick a point and use the triangle inequality on y. So for any x, the triangle inequality. Again, this is for the space Y. Shows that if we look at, I want to look at the distance between F and H. That's the distance in Y. That's at most the distance from F of X to G of X, plus the distance from G of X to H of X. Okay. Those two are both bounded above by the uniform metric on those functions. So, this thing, the sum of the uniform metrics of, well, the uniform metric comparing F and G and plus the one comparing G and H is always an upper bound on the things in the set that define the uniform metric of F and H. So let me try and write this. Thus, this quantity is an upper bound on that set. Okay, because this holds for every single X. That's what we proved. And that gives us what we want. That proves the triangle inequality. Any questions on that proof?
Why can't you just go directly and say that F and H is also less than the supremum metric, uniform metric? And I guess you don't know the relationship with that and the additions, so you need this extra piece.
Yeah, I mean, you could just you could definitely write this differently. Is that your question? Where you could just kind of start with this, expand it out as a supremum, use this upper bound.
No, I just meant we know that dy f of h is also less than the infinity f of h, right? But that's not enough to piece together that inequality.
Oh, right. So we do know that, but that won't give you this inequality, yeah. Definitely, so if you think about it, definitely we have to use the triangle inequality on Y. Otherwise, it's not going to be true. Okay.
I'm a little confused here. So we're saying that the d infinity fg plus d infinity gh is an upper bound of dy of this specific x value?
That's a
And then
set.
there's-
That's a set.
Right. Okay.
That's a set for all x, and that's the set in the definition of D infinity.
So since this is an upper bound for this set, the supremum is less than or equal to it.
Yep.
Okay.
Okay, so our whole reason for introducing this is, I claimed at the beginning of lecture, that uniform convergence is going to be the same as convergence in this metric. So let's prove that next, okay? If we've got a sequence, oops, should need to give it a name. We've got a sequence Fn of bounded functions. That converges to a function f in the metric space we've just defined. If and only if, and now we're going to talk about the old kind of convergence. This sequence Fn converges uniformly to F. Okay. Questions about the statement?
So here we're talking about how a property of these f's inside a metric space is related to these f's outside of the metric spaces. Like f's act between metric spaces, but here we're talking about f as elements of metric spaces.
So in the first part of the statement, the functions are in that metric space. Oops. In the first part of the statement, we're thinking about the functions in the metric space. In the second part of the statement of this theorem, we're thinking about uniform convergence from Friday.
Okay.
Okay. If and only if, so we got those two directions. They're both really actually easy. So first, suppose that we have convergence in the new metric space. Okay. Now, we just have to think about what that means. That means our standard notion of convergence in metric spaces, which is for any epsilon, there is a capital N, blah, blah, blah. So given epsilon, there is a capital N such that if N is at least capital N, then the distance, and now we're measuring distance in the uniform metric. The distance between Fn and F is less than epsilon. Okay, so again, that's the definition of convergence in a metric space. And now we use the definition of what the uniform metric really is. So in particular, for every n at least capital N and x in x, what do we have? The distance in y between Fn of x and f of x is, by definition, and that's at most the uniform metric distance between Fn and f, and we just said that is less than epsilon. Okay. What we just wrote down is the very definition of uniform convergence. Okay, the other direction is basically the same thing, except going the other way. Conversely, let's see if we can go through this a little bit quickly, because we do have one more result after this. Let's say we do have uniform convergence. Now what that means, this is back to Friday's definition, given epsilon, there is a capital N, so that for every little n, at least capital N, and every point x in x, the distance in y between Fn and Fn of x and f of x is less than epsilon. Now, what does that mean? In terms of the infinity metric.
The supremum is also less than epsilon.
Is that true?
Less than or equal.
Yeah. If all of the members of a set are less than something, you can conclude that the supremum is less than or equal to that number.
Well, yes, by definition of the supremum.
Yeah. But I'm pointing out that that's a less than or equal to. Not a less than. And let me add the quantifier there, and we'll come back to this in a second. Therefore, this is true for all n at least capital N. And thus, Fn converges to F in the new metric space. And that's what we wanted. So we're done. Are there any complaints?
Yeah, I don't like this equal to.
Yeah. So normally we'd have a strict one there, right?
But can't we just do like the epsilon we pick for the uniform convergence? Can't we just do like epsilon plus 1, and then for any epsilon we're less than, or something like that?
Yeah, so here's the point. Normally we have a strict inequality there. This doesn't matter. It doesn't matter if it's weak or strict. I feel like we did this exercise last semester. Yeah, I'm going to get to your suggestions here in a second, Benjamin. But I feel like we did this trick last semester where in that definition, it really doesn't matter because you can divide epsilon by 2 or multiply it by 2 to go back and forth between weak and strong. What we could do here, we could say, given an epsilon greater than 0, there is a capital N such that this distance is less than epsilon over 2. And then we'd come down here and we'd say, okay, this supremum is less than or equal to epsilon over 2. But that's less than epsilon. So we're fine. Okay? So what I did in red there is one way to fix this issue of where the definition technically has a strict inequality and we technically gave it a weak inequality. But more than that, what I said over here in the pink is that this never matters. And just think about it, you know, in a metric space, what is convergence? It's that you're getting, your sequence is getting so close that no matter what number you pick, the sequence will get within that distance to the limit. Well, it doesn't matter for that definition if that's a strong or a strict or a weak inequality. You're still getting as close as you're getting as close as you could want to the limit. Okay. Benjamin asked in the chat, are we assuming that the functions fn are bounded? Yes, we are. We said in the hypotheses that the sequence fn comes from b of x, y, and so they're all bounded. We don't know that they're uniformly bounded. This goes back to an exercise from the last lecture. Okay, but I'll just leave that at that. It doesn't matter right now. Okay, any other questions before we move on? We've got one more result.
I've got a question about the way we're writing these sequences.
Uh-huh.
So we use the same symbol, the parentheses fn, for the sequence in this the bounded metric space, and also for just sort of our other notion of sequence. Like they're two different sequences, but they're written the same way. Is there a better way to denote the difference, or do we just have to be careful with stating the context?
Yeah, I see your question. Yeah, boy, I was about to say they're the same sequence. It just matters about where you look at. But I think technically that's not actually true. They're different sequences with the same notation. So I think you're just gonna, if that bothers you, you're just gonna have to say that which sequence you're talking about has to be inferred from the context. anyone is confused by that comment, don't worry about it. It doesn't really matter. But we're talking about the difference between the first FN sequence and the second FN sequence here. Whereas one could make a case that they're different objects. Okay? But morally, I would say don't make that case. Don't make that distinction. They're the same thing. Okay?
Suppose I did want to give them a different name. Could I do like, just do like a star? Like parentheses FN, like star is this one, and then the other one is unstarred? Something like that, or is that gonna, strays too much from the norm?
I've never seen anyone make that kind of a distinction.
Okay.
So I would not.
Okay.
It's not like we're changing the function, right? Oh, okay, sorry. I have a more refined version of the answer I wanted to give earlier. The functions Fn are the same. Okay, a function consists of a domain, a codomain, it is an association between a domain and a codomain. Or if you want to get all set theory about it, it's a function is a domain, a codomain, and a set of ordered pairs. Okay? Satisfying certain axioms. So those functions, the Fn, are exactly the same. Those are exactly the same object. The sequence of the Fn's then are, again, exactly the same. Whether you look at that sequence as lying in this metric space or not lying in the metric space, it doesn't matter. It's the same sequence. Do you buy that answer?
Yeah, I see that they are the same, and even here with this proof, it even shows that they're even more the same.
Yeah.
Like this. Okay, it makes sense. I buy it.
Okay. So what did we just show? Oh, so we just showed, like we promised, uniform convergence in the uniform metric is the same as uniform convergence. That is the whole justification for this metric. Now, what we haven't done is actually prove a result about this metric space. Right? We've just shown how we can interpret things here. Let's prove a result. If we have time, we might only get halfway through. First, we're often only interested in the continuous functions here. So far, we've just been talking about the bounded functions. So we're going to define the continuous functions to be a subset here. So I will write this as C of xy this is a continuous bounded function from x y. And of course, this is a subset of our bounded functions. Okay. We're not going to, we're not going to make a big deal about which set the uniform metric is defined on. So let me just note that we can do the uniform metric here too. So continuous bounded functions from x to y with that uniform metric, that's also a metric space. Okay. It's also, just going back to a comment from the beginning of the lecture, if y happens to be a field, like if y is the real numbers or the complex numbers or something, this is also a vector space, just like the bounded functions were a vector space. This is an even more interesting vector space. What's the basis here? I'll leave that to you to ponder. Okay? Now, any questions on that definition? No? Okay. Let's suppose that x and y are metric spaces. And one more hypothesis. We want y to be complete. Okay. Remember, the definition of complete is sequences that should converge, do converge, or Cauchy sequences. Cauchy sequences converge. Oops. Then our theorem says, in the uniform metric, the space of continuous functions from x to y is also complete. Now, unfortunately, we're not going to have time to do the whole proof here. Let me point out that part of this is going back to the result from Monday, that if you have a sequence of continuous functions and it converges uniformly, then the uniform limit there is also continuous. Okay. So if we do have a sequence that's converging in this metric space, so think, if we do have a sequence that converges in this metric space, then by the result we just proved, that means that the sequence is converging uniformly. And by the result from Monday, that means that the sequence is converging uniformly to a continuous function, and therefore the limit of that sequence is also in this space. Okay, that has nothing to do with the proof of this. That's just an observation to make. I mean, if that weren't true, then this result wouldn't be true. Okay. So we have time to start this proof, and then I'm gonna have to refer to the lecture notes for the conclusion of the proof. Okay. So we're gonna suppose that we know that y is complete. Okay. And we need to take a Cauchy sequence. So suppose that Fn is a Cauchy sequence in our space of continuous functions with the uniform metric. Now, the first question you should have is, I mean, do we even have a pointwise limit? And again, you go back to, I think it was Friday's lecture, we talked about if you're going to have a uniform limit, the uniform limit has to be your pointwise limit. So you should always first ask, do I have a pointwise limit? Well, do we have a pointwise limit? For any point x, we look at the sequence of function values there. And our claim is that that sequence is Cauchy in Y. Why is that true? I'll write it over here on the side. If you're looking at the distance between Fn of x and Fm of x, your upper bound on that would be, it's at most the uniform metric distance between Fn and Fm. Okay. Why is that true? Well, because x is one of the points in the domain. Okay. So therefore, there is some function we can define. So the sequence of functions converges pointwise to some function f. Okay? Now, that's where I'm going to have to leave the proof. That's about halfway through the proof. What we haven't shown here, we haven't said that f is continuous. We're actually never going to say that. What we need to prove now is that this convergence is actually uniform. And it's really just going through the definitions. Okay? So the next thing here is get uniform convergence. Okay? And once you have uniform convergence, then by our result from last lecture, you know that f is actually continuous, so it's actually in that space. Okay, and that's all you need to show, is that Cauchy sequences converge. Okay, any last questions? Like I said, the whole proof of that will be in the lecture notes, or it's in Tao's book as well. Okay. Well, I will see you all on Friday. Have a good rest of the week. Until then.